Today, we're going to look at cloud-based approaches to facilitating communication with mobile applications. We're going to talk about the general problem that we're attempting to address, and then look at some of the more commonplace approaches to dealing with communication concerns. Generally, a mobile application oftentimes needs to fetch information from external sources. Many times, that external source might be some cloud service where, of course, the cloud is just somebody else's computer, and we can have data uh, housed in services available on the internet that an application may need to communicate with. And sometimes we just need to have our mobile devices or our applications running on those mobile devices communicating with other instances of that mobile application running on another device. So there are quite a few ways that you can facilitate communication between two devices, but oftentimes there are geographic concerns that prevent direct communication between such instances of an application. So, what is oftentimes the case is that the cloud can be used as an intermediary, allowing communication from one system, one instance of your application to another. So, whether your application needs to get data from a cloud service or from another application, we can generally access the internet as a way to do this. When it comes to accessing information that is housed, whether directly or indirectly, via a cloud-based interface, i.e., when we're accessing the internet to get information, the more common approaches that exist tend to be built on either a pull model or a push model. A pull model is where the client or the mobile application running on a mobile device reaches out to the internet-based service, requesting new data and then pulling it in to be used by the application. This is oftentimes referred to as polling, where the polling implies that that check occurs on a frequent and recurring basis. Simple applications that tend to use polling solutions are some email protocols like POP3, oftentimes fetching things like stock quotes from third-party web services requires that the application essentially hit the website, hit the web server, and pull the data in at some predetermined period. And pretty much any service that makes data available via RSS or real simple syndication. So podcasts, for example, are published via RSS, and most podcast applications will read an RSS feed and poll that RSS feed again at some predetermined time period to check for the availability of new podcasts. And then processing that RSS feed, it will download the audio file or download the video file and then allow the user to play that content. When using polling, there are some considerations that we have to keep in mind. First, polling is not real time. That basically means that your client may not be made aware of data, new data, the moment it becomes available. Instead, the client is only made aware of new information when it does its own check, when it polls. That means for some important data, if an update is needed quickly, polling may not be the most ideal solution. Polling can also consume excessive resources by some definition of excessive. It can cause this because a simple client may hit a service numerous times, even though there is no new data for the client to fetch, but it would not know that until after it has checked. And in a scenario where many clients are hitting the server continuously, that can cause a depletion of server resources or server availability. One solution to this is to implement what's called exponential backoff. Exponential backoff is a solution where when a client hits the web service to fetch information, there is some time period that must expire between one check and the next check. And exponential backoff simply says that the time that we wait will continuously increase exponentially in theory, but in reality, it really doesn't matter as long as there is a continuous increase. And this is basically triggered, or the increase is triggered by the unavailability of data. So if the client checks at a particular time period and there is no information available, it will check again. Let us say that this was 60 seconds. It will check again in another 60 seconds. If it sees no information, then next time it'll wait 2 minutes. If it still sees no information, then it waits 4 minutes. And so on and so forth until we get to some predetermined upper limit, and the service can keep checking at that extended period, so maybe every hour. On the other side, if data is ever found at any particular interval, then exponential backoff algorithms then tend to reset the time counter, and we start to check again at a more frequently, and we essentially just reset the backoff counter. So if we found information when we checked at minute 16, then we go back to doing a 60-second interval check. The rationale there is that if some data is available now, more data may be available again soon. So obviously that depends on the specific use case. Are you in an active interaction where the presence of new information suggests more data will be coming in soon? Or is it a scenario where, having received data, you can almost be certain that you will not get another update for an extended period of time? So the solution that you implement really does depend on the use case. It depends on the type of solution you are building. One of the benefits to polling is that it is relatively easy to implement. Exponential backoff aside, ultimately building polling solutions just means taking whatever logic that you have to hit the server and pull data down and putting that in some kind of loop structure. If you've done that, you have a polling solution. Again, exponential backoff is something you could then potentially integrate to make your system a little smarter. Now, polling by itself is perhaps the most basic of the solutions that we have, but it is still used today. It's still very commonplace because there are times where you really can't get around polling. For example, if a protocol is already established, such as RSS, news feeds, email, etc., and you're building an application that needs to integrate, then your only option, more or less, is to create a wrapper around the service that essentially just keeps checking the server for new data. If you cannot go in and modify the protocol to implement some sort of push technology, which we're going to talk about next, then you just have to keep doing what is allowed over and over and over again. This is especially the case if you do not control the infrastructure or the data. So if it is some third party and they do not facilitate any kind of push, then polling is all you have available. So it's always a good idea to understand polling, the different approaches, solutions that you can implement, and ensure that that is just a tool that you have available. Next up, we have what is oftentimes referred to as push technology or push services. Push is when the server informs the client when new data is available. This is in contrast to the client having to check the service at a predetermined period of time. This means that the client is not checking the server unnecessarily, which can consume resources because the server now needs to generate responses to all the clients that are checking for the availability of data, even if there is no data available. So for us, that basically looks like some data becoming available. And when that happens, the service via the cloud, via the internet, pushes data to the client or to multiple clients. And once upon receipt, the clients can then process that information per whatever it is the application is meant to do with it. Now, while push technology becomes possible and in some ways practical when the limitations we mentioned before are not present, push is still not a panacea. It doesn't solve everything, and it's not always the best solution or even possible, despite some of the other components being there, such as you having access to or control of the server and the data. There are still considerations that come into play. For instance, it is the case that for push solutions to take effect, the server must have a path to the client. This can prove difficult when a client is behind a firewall or a router implementing NAT, or referred to as network address translation. The situation we have is, while we might take the abstract view of the server being able to access the clients directly, in reality what happens is that somewhere in between there is some router, some network, something that allows the clients to access the internet, and ultimately it houses all these clients on a private network. Private network has a set of reserved IP addresses. They usually take the form of something like 10 dot something or 192 dot something or 172 dot something. These IP addresses cannot be accessed from external resources. So a server cannot access a client via its 10.0 IP. Instead, it can only get direct access to, here I'm just referring to it as through the router, through the gateway. And the gateway is what will have a public IP address. Now, it was not mentioned explicitly, but one of the benefits of a server being on the internet, or just a cloud service in general, is that that is also publicly accessible. It's what allows pull technologies to work. The client can always access a cloud-based server, but the reverse is not true. So in order for our client to be accessed by the server, we more or less have to punch a hole through the router. This is, punching a hole is not the technical term, but what has to happen is that the router has to facilitate or allow for a connection to be established. And with current IP4 technologies, that generally means the client has to first establish a connection with the server. And we have to basically keep that connection open. Once the connection is open, the router, whenever it sees data from a previously established connection, will know that it should be sent to a particular client and then route that information there. There are other ways this can be done. Usually that is how we implement servers on a private network. But a mobile device just being connected over Wi-Fi, the only real practical solution is NAT. So this does place some amount of some technical requirements on what we can implement or how we would implement push technologies. And we therefore must be mindful of the fact that there are different scenarios that can impact the reliability of that connection. Now, one of the solutions that is meant to address some of the technical implementations or technical requirements of getting push technologies to work is what we call Extensible Messaging and Presence Protocol, or XMPP. So XMPP is an open protocol. Anyone can review it and implement it. It is a protocol that provides near real-time communication between clients, regardless of who those clients are, whether those are servers, mobile devices, desktops. XMPP can be implemented in any client that wants to communicate over a network connection. And XMPP, for what it's worth, is an XML-based protocol. So all the content being transmitted is marshaled and then sent over as an XML document. Here we have a very basic, very straightforward illustration of how XMPP works. First, what we have is a mobile client that has an application that has implemented XMPP in some way. We have an application server that is on the cloud, in the cloud, along with an XMPP server. So these are just services, entities. They could be on the same machine, different machines. It really doesn't matter. And we have some notion of a database keeping track of some information. So the flow goes, when new data is available, that information is made available to the application server, and it will then notify the client, or push a notification to the client via the XMPP server, making the client aware. It may choose to either send the data directly or simply inform the client and then have the client fetch the information from the server directly, depending on the type of data and how much data needs to be transmitted. As mentioned, XMPP uses XML. So if the payload can be included with the push notification, then that would save a step. Otherwise, it can again just serve as a way to notify the client that more data is available, or that data is available, new information, and the client can fetch from the application server. Now, when using XMPP, there are some things to keep in mind. First, every entity is a client. In other words, there is really no distinction between a server, the application server that is, and the client instance, so the app running on the mobile device. They're all simply assigned IDs, or they're all seen as clients of the server, of the XMPP server, all assigned IDs, and then they are just communicating with each other by sending messages. Because of this, your application server may need to keep track of client IDs in order to send direct messages. So this will impact the way you design and build your application server, because we now have to keep track of this additional unique identifier for a particular client, in addition to whatever unique identifier you are potentially keeping track of for your own application's needs. And even though XMPP sort of streamlines the ability to deliver the message, there are no guarantees that the client will necessarily be connected at any given time. However, XMPP will, through its own implementation, automatically queue messages for a period of time. I believe it's 4 weeks, but whatever the number is, it can be changed. And then the client will respond or receive the message once it comes online, once it becomes available. This means you need to be able to have your client discern the relevance of a message when it is received. For example, a message that is letting a client know about a news story, for instance, may be very useful, and the application may want to respond by popping up a notification to the user when the message is freshly received. That is, if the event just occurred. But if a message is queued for 4 weeks and then the client, the device running the application is then turned on and the message is delivered at that point, that, one could argue, is no longer news, and the application may not want to push a notification to the user. So including information or having your client process the data with the consideration of how long ago this message was created is also perhaps a necessary step that you will want to implement. Now, one of the scenarios that we have to contend with XMPP on Android is that it is not natively supported. That being said, there are a few libraries that are available. Some amount of complexity is involved in implementing them, but it can be done. XMPP also has the not exactly unique, but certainly prevalent characteristic of depleting resources, specifically batteries. This occurs because you can imagine if you have multiple clients, multiple applications on a single device, all speaking with different web services via XMPP, all attempting to stay connected continuously, that is going to put a strain on your battery, because trying to keep those internet connections open is ultimately not an ideal situation for a mobile device. There are the three main drivers for battery consumption on a mobile device are your screen, GPS, and your network. As long as those are running, your battery is being eaten through. So trying to keep your connection open and trying to keep multiple connections open is going to be problematic. And of course, on the back end, utilizing XMPP requires an XMPP server and the subsequent integration with your application server. So whatever is maintaining your own application logic and APIs and databases, you will need to factor in an XMPP server. And as mentioned before, considerations for things like the XMPP IDs for each of the clients. So there is some work involved in implementing and maintaining this system. The good thing is that many, if not most, I wouldn't want to say all, but certainly many and most, of the XMPP servers available out there are in fact free. So you can simply evaluate and install one and then go through, make a determination of which one is easier to integrate, which one is easier to maintain, and move from there. So again, XMPP on Android is a tall order. It's not a simple solution, but it does give you depending on what your non-functional requirements are, it does meet the requirement of allowing a server to push information to a client. Now, if we want to have the benefits of XMPP, but we want to reduce some of the technical debt, some of the technical considerations that come along with it, there is another approach that we can utilize. On Android and for other platforms, there is a service that is built on top of XMPP, and therefore comes with a lot of the benefits. That is things like allowing for routing to any client that has an ID, determining or being able to send a payload in a message via a push notification, or just informing the client and having the client then fetch the data, queuing messages for a period of time, etc. And that solution is, in some sense, a little more straightforward to implement because it is, first and foremost, maintained and operated by Google. And that solution is called Firebase Cloud Messaging. So Firebase Cloud Messaging is a part of the Google Play Services, or whatever the new umbrella term is. I believe they've just called, now it's just a part of Firebase. It allows message delivery from server to client or vice versa, so we can go both ways. And as I mentioned a moment ago, it can be used to send a notification or to pass a message directly. The different use cases here are called send to sync versus message with payload. Now, the reason that Firebase Cloud Messaging, or FCM, which is built on top of the XMPP protocol, the reason this actually works, the idea behind it is that all applications running on a single device that use FCM are all sharing the same pipe, the same connection. So if 50 applications implement FCM, your device is only maintaining one active connection to Google's FCM server, their XMPP server, instead of all 50 applications maintaining 50 different connections. Additionally, FCM will queue messages locally, but what's more is, even if your application is not running with no direct connection, when an FCM message is received, it will still be handed over to your application. Your app is basically woken up, and the message delivered for your app to process, and then you can decide on how that what happens in your application. Anything from running a job, performing some work, to just letting the user know that something occurred by popping a notification up. And the content that is delivered via FCM is JSON based versus the XML of XMPP, where in this scenario, it's arguable that JSON is a little easier to process in an Android application. So here we see the general flow where instead of our XMPP server, we are replacing that with what was originally called the Google Cloud Messaging, and I still have that image here, but it's now been rebranded to Firebase Cloud Messaging. But we can see it's the same flow, where when data becomes available, it is sent to the application server. The application server now, instead of using XMPP, goes to Google Cloud Messaging. The data is then sent to the client, which can then either process the data that is sent via a payload, or it fetches it from the application server. Once again, the application server is going to be able to, or it will be necessary potentially, to maintain things like the IDs of each of the application instances, so that you can send direct messages if that is what's necessary in your application. So what we're going to look at next is implementing Firebase in a mobile app.